Welcome back, class. We are starting our new chapter, which is actually about the continuous time, linear time invariant systems. In last chapter, we have studied about the general characteristics of the signals, transformations, checking that whether our signals are periodic or non-periodic, different kinds of the common signals which are used in the engineering systems, unit step, rectangular, impulse, triangular, and lastly we see the continuous system, and we have seen different properties of the continuous time systems. Okay, like about the memory, causality, invertibility, time invariance, stability. So this chapter is focused on the continuous time, linear time invariant system. So now we will be dealing with the CT, continuous time, and our system will be linear and also it will be time invariant. Okay, we have learned that what are the characteristics for the time invariant, that if your input is have a shifted, if you are making shift in the input, you should get the same shift at the output. Okay, so then your system will be time invariant. Linear system is, we learned in the last chapter, okay, that if you are additivity and homogeneity properties, okay, so in the, if you are like adding two inputs, okay, your individual outputs should also be added with the same, okay, the integers multipliers. Okay, so that was the linear properties. So this chapter we are going to see some more properties, okay, of the LTI system. Okay, linear time invariant system, we call them continuous time LTI system, linear time invariant system. Okay, so let's say, so LTI systems are very important. Okay, the linear time invariant systems are widely used, okay, and for the wide range of applications, okay, in the signal systems, in the control systems, in digital systems, digital signal processing. Okay, there are a lot of applications, the linear time invariant system. Okay, we have seen earlier on, okay, what is the time invariant property, as I was just explaining. If simple input is producing y of t, then the shifted input would produce the y of t minus t naught. This is the time invariant property, and the linear property is this one, okay, which I just explained. So the combining these two make the linear time invariant system. So this is just a brief review, okay, what we have studied in the last time. Now we are going to study about the impulse representation of signals, that how we can represent signals in the form of impulse. Okay, what does this mean? So before going into this, let's quickly review some properties of the impulse which we have studied in the last chapter. So the very important property of the impulse is, if you multiply impulse with any function, we will get the function value at the impulse location with that impulse, right? And this another property was, if you integrate this one, if you just integrate impulse, okay, from minus infinity to infinity dt, it will be 1. If you integrate this one, so you will get the function value at that location only, and because integration will be 1. Okay, so these are the properties of the simple properties of the impulse system. Now let's say we have a system, okay, and this is an LTI system. Okay, this is my input, and for this input I am getting this output of the LTI system. Okay, now let's say if our input is impulse, our input is impulse. Okay, now the output of this system, okay, or the response of this system, will be called as impulse response. So we are going to use this word again and again. Okay, so the response of the system or output of the system when the input is impulse is called impulse response of the system, and we usually represent using the h of t. Okay, so if you have input sigma of t, it will give you impulse response of h of t. If you have a shifted input, it will give you shifted impulse response. It will give me shifted impulse response of the system. Okay, so how we are actually getting this thing? Okay, so now if you want to get, okay, the original input, okay, so we know that this is impulse property, that when a function multiply with the shifted impulse, so what will be happening? Okay, we will get the function value at the impulse location. So remember here the variable is tau. Okay, so basically I can rewrite this thing as x of tau, and here the variable is tau, so minus tau into plus t here into d tau. Okay, so the variable is tau, so basically what will be happening here, I will get the function value at the impulse location. So impulse location is t, so I will get x of t. Okay, and then the integration of the impulse into data, integration of the impulse for the complete interval is 1, so I will get my original input. Okay, so this property, so this is just the representation of this property in the another variable form. Okay, so this is called impulse representation of the signals. Okay, we can represent our signal in the form of impulse. We can represent our signal in the form of impulse here. Okay, so this representation is called the impulse representation of my system. Okay, now let's try to solve, we will solve the examples related to the finding the impulse response of the system. Okay, for example, let's say this is my input, let's say this is the response of the system. Okay, now let's say if the input is sigma of t, okay, then what would be the response of the system or the impulse response? Okay, so let's just replace our input with the impulse, so it will be sine of 2t times sigma of t, and then this impulse is existing at t is equal to 0, right? So we will get the function value at the impulse location, which is 0 times sigma of t, or sine of 0, we know that sine of 0 will be 0. Okay, so 0 multiplied by impulse, it will be 0. So that is the actually impulse response of this system. If the input is impulse, then the impulse response of this system is 0. Okay, so we will solve a couple of more examples during the live session. Okay, now let's say I have a system. Okay, I have a system or LTI system where impulse response is given by this. Okay, this is the impulse response. Okay, now if I have one input, okay, and I will get output with the interaction of this impulse response. Okay, so the interaction between the input and impulse response of the system, okay, their interaction is called convolution. This is very important concept, convolution concept, and a lot of applications for this concept in the signal and systems, digital signal processing, artificial intelligence, okay, you name it. Okay, so this is very important concept. Okay, so mathematically what we are actually doing here, the interaction between your input and your impulse response, okay, that is called convolution, and mathematically we represent like this one, that we have input, okay, and I am multiplying with the shifted impulse response, okay, and I am integrating for the complete time interval. Okay, so what I am doing, I have input, I am multiplying with the shifted impulse response, and I am integrating for the complete time interval, and I will get the output. So here there is one very important thing, the shift could be in the impulse response or the shift could be in the input system. So I could also have, because this is linear time invariant system, so I could have like t minus tau into h of tau into data. So whether I bring shift in the input or the impulse response, the response of the output will not change. Okay, so this is the integral forms, okay, or we can also represent this thing that this is the convolution between the input and the between the input and the impulse response. So we use this symbol to represent the convolution of the system. Okay. So usually we do the convolution using the graphical form. Okay. So for the graphical representation of the convolution, there are different steps. Okay. So I will try to explain the concept with the help of the examples. Okay. So let's say this is my input x of t, this rectangular system. Okay, and this is another rectangular function. Okay, let's say this is the impulse response and I want to get the output. So this signal is representing my input and this signal is representing my output. Okay, so for the graphical representation, the first step is that we change our variables, okay, to the different variable tau. Okay, that is the first step. Okay, so we will write the function in the form of tau. Okay, the same function, okay, input and the output, but we are writing in the form of the tau. This is now tau except h of tau. Okay, then the second step is we will flip over any one of them. Okay, you can either flip x of tau or h of tau, whatever you like. Okay, so usually it's easier to flip the shorter signal. So whichever signal is shorter or more simpler, okay, you can flip that. Okay, so for example, I'm going to flip here. So flip means I'm going to take the time time reversal of this system. Okay, so this is h of tau. I'm going to calculate h of minus tau here. Okay, so this will be just flipping, okay, around the vertical axis. Okay, so this is the second step. Okay, the next what we are going to do, okay, now we are going to overlap this flipped signal with this, okay, for the different time intervals, and then we are going to integrate for those time intervals. Okay, how we are going to do this thing? Okay, I will solve this during the live session because this will be more clear once we solve this in the live session. Okay, but before that I have one homework for you. Okay, you guys have to plot. Okay, let's say this is my hf minus tau. Now let's say I want to plot this hf minus tau for this signal, let's say -2, and let's say -2, I want to shift this -2 minus tau. Okay, plot this. What will be the plot of this one? And then plot this one, 2 minus tau. How the plot of this one will look like? This is the h of minus tau, and try to plot h of -2 minus tau and 2 minus tau. Okay, then we will discuss in the live session that how we can actually convolve these two signals so that we can get the final results. Okay, thank you very much for your time here. We will solve this during the live session. So this is actually the till this is the graphical representation, that how using the graphical way we can calculate the convolution of the two signals. Okay, thank you very much. See you in live session.